Welcome to the Kinetic Energy Lab, where we'll be analyzing how the energy of this ball changes as it rolls down this ramp. So, our wild guess question involved a certain height. How fast is a ball going if we drop it from a certain height? Now, they have different variables for different classes, but there was a number there, 1.5 meters or 2 meters. How fast is it going when we drop it from that height? Now, dropping it this way does not give us a useful way to measure the velocity at the bottom. It also doesn't matter if we drop something straight down or if we roll it down the ramp. Either way, it had the same amount of gravitational potential energy to start. It requires gravitational potential energy it requires my energy to lift this up, and now it has gravitational potential energy stored in it because of its distance away from the ground. When we first did the ball on ramp labs, we rolled the ball down the ramp and we saw how long it took to go different distances. We found the relationship between distance and time by measuring distances and time. That relationship on the floor was a linear one. Where for every second traveled, it travels more distance. And we got the equation d equals v times t, or v equals d over t. Those are the same equation. It's our basic equation for velocity, right? Distance over time, meters per second, miles per hour, it's all connected. Then in our second ball and ramp lab, we analyzed how far it went different distances while it was on the ramp, how long it took to go, 1 meter, 2 meters, 3 meters. And then we found the relationship between distance and time while an object was accelerating, which is a quadratic relationship, because the more time it goes, the way more distance it goes, because it's speeding up. So if we go twice the time, it'll go 4 times the distance. That's what happens with a quadratic relationship. A lot of people's research extension questions on these labs was, what happens if I change the height of the ramp? Because for that lab, we kept it at a constant 20 centimeters, or something like that. So we had a constant ramp height, and we were finding the relationship between distance and time. Now we've got that relationship. We want to find the relationship between the gravitational potential energy and the kinetic energy at the bottom. Now we know, if we're just talking about the energies, that it has to be the same. I can give this ball energy by using my own stored energy to lift it up away from the ground. As soon as I release it onto this ramp, it will be conserved. Whatever gravitational potential energy it has here at the top, it's going to have the same amount of energy at the bottom, but it's going to be all kinetic because it's now totally on the floor. It has no distance away from the ground. So our equation for this was mass times gravity times height. Mass times 10 meters per second, that's the gravity here on Earth. If you want a different number for that gravity value, you'll have to go to the moon or Mars. So times height. So the amount of height it has matters for how much potential energy it has. So what we're going to do, we're going to roll the ball down the ramp, and we're going to time from the bottom of the ramp to 2 meters, how long it takes to travel 2 meters at the bottom of the ramp. Why are we doing that? We're finding the velocity of the ball when it reaches the bottom. Distance divided by time. 2 divided by each one of your different times will give you the velocity at the bottom of the ramp. We can find the connection between velocity, which we know is involved in kinetic energy. Things have kinetic energy if they're moving, and if they're moving faster, they have more kinetic energy, right? So we're going to find the relationship between the height of the ramp and the velocity that the ball is going along the bottom. So we crucially, listing in your procedure, we want to say that we change the height of the ramp, right? Because that's our independent variable. So we change the height of the ramp, and then we measure how long it takes to go 2 meters. So we have a few different controls here. You'll want to know the mass of the ball, because I'm pretty sure that's involved with potential energy and kinetic energy, because things that are more massive are harder to lift. And when something is harder to lift, it has more potential energy, because when we drop it, it's going to hit really hard down on the ground if it's super massive. Same with kinetic energy. If something is moving faster, it definitely has more kinetic energy. But also if something is more massive, it has more kinetic energy. Think of a car going 5 miles an hour or a bike going 5 miles an hour. One of these would require a lot less energy to stop, right? We can also get a bullet to have the same kinetic energy as a car. If the bullet is traveling very, very fast and the car is massive but traveling very slow, we can make those line up. But we're going to find the exact relationship between the height of the ramp, the height I drop something, and how fast it's going at the bottom. Let's go check this out on paper. A good procedure drawing should not simply be the ramp and the ball and the height building thing that we had. It should also include all of the measurements that we're taking. So for example, here's the height. We want to label it. We're measuring different heights. What else do we measure? The distance that it traveled, right? 2 meters, so that we could use v equals d over t to solve for the velocity at the bottom of the ramp. We also, it'd be nice, I like to draw a little clock around here to show that we are timing how long it goes 2 meters. It takes to go 2 meters. So this is what a good procedure drawing should look like with all of these labeled. And then when you go to value of controls, you would say things like the mass of the ball and the 2 meters that we kept the same and the length of the ramp. Those would all be good values of controls for this case. So let's talk about what the energies are going on here. So we're starting with gravitational potential energy, which is based on 3 factors. It's based on the mass of the object, it's based on the g, the acceleration due to gravity, and it's based on the height. All 3 of those things multiplied together are going to give us our gravitational potential energy, and that's measured in joules. So g is 10 meters per second everywhere here on Earth. If you want to get a different acceleration due to gravity, you'll need to go to the moon or to Mars. And then our mass is constant, right? It's one of our values of controls. In fact, it'd be nice to even write it here. Mass equals 0.066 kilograms. So we've got our mass, we've got our g. What we're changing is our height. And we want to find the relationship between this height and this velocity. So we're going to end up with some equation. It's based on GPE equals KE. And if we can get this equation down, it's going to tell us how velocity connects to kinetic energy. So what we're going to end up with is a variable here, an h, a height, or the full GPE. And the result will be the kinetic energy. And you're going to get h equals, you're going to get some number times v squared. This is our relationship. And using this relationship, we can now go back and solve the wild guess question. Absolutely crucial to do that. We plug that height in for one of these 2 variables. I'm not going to tell you which. And we solve for the other variable. Because ultimately, our MGH equaled our KE. Now the application of this is that our equation for kinetic energy involves a squared velocity. And in fact, it's 1/2 times the mass times the velocity squared. And shorthand, KE equals 1/2 mv squared. We'll be using both of these equations, GPE, mass g times height, and KE equals 1/2 mv squared on our tests and other things.